Hello, everybody. Thank you for having us. Our group is Wad Accuracy Effects. Our group members are Joseph Porto, Henry Bergeron, and Will Leiphart. Test objective. Our goal is to find a shotgun shell wad that is the most consistent and accurate. Not all shell wads are consistent with how they shoot, and we want to find the shell that is most consistent and cost effective. Our key question, how does the consistency and accuracy of shotgun shell patterns vary between different wad types, and what characteristics contribute to the most accurate and uniform shot spread? Our background and prior work. WADs impact shot spread, accuracy, and downrange performance. Designs are proprietary and tailored to specific uses based on industry needs and wants. Most research is manufacturer-led and not independently verified. And therefore, key variables like pedal deployment and dispersion repeatability are often ignored. And shooters often rely on anecdotal info, not real data, when they have to choose their ammo. For these reasons, our significance and impacts, our project shows how different WAD designs directly influence shot pattern, spread, and accuracy, something that hasn't been well documented and is, for the most part, biased in most company research. We're addressing a clear gap in the industry and by running independent side-by-side comparisons of the WADs and their performance across different brands and their different WAD geometries. This will hopefully help hunters and sports shooters move beyond what the market claims is the best wad or what the market claims is the best shell, and they can move past that anecdotal advice and choose ammo based on real, legit data. Manufacturers could also benefit from our research by making clearer benchmarks and potentially leading to better and more consistent product designs. Lastly, by identifying more effective or more efficient wads, we could encourage a shift towards options with less environmental impacts, such as biodegradable materials. For sustainability, um, our our project provides lasting, reusable data on WAD performance for future testing and for future reference. We're hoping to reduce the reliance on trial and error shooting by offering standardized performance and insights. And our approach for said sustainability is to use the Shotgun Pattern Containment Index, otherwise known as SPCI. We're going to use this index, we're going to use this metric to quantify how tightly and consistently shot patterns group on a target. This metric will allow us to objectively compare watt performance across the different brands using repeatable, data-driven evidence.
Our theoretical results for our hypothesis, we expect the black cloud wad to have the most accurate and the highest SBCI throughout testing. In our federal Top Gun shell, we expect it to have the least and lowest SPCI throughout our testing due to the fact that it's just the cheapest shell on the market and sort of just the base buy. And then our second and third, we expect to be Kent and Winchester due to the quality and similarities in their wads. The Black Cloud has a unique wad and it splits in the back. It doesn't open in the front here, and it just only opens in the back. So it sort of keeps the BBs in a tighter spread throughout, and it's supposed to have a higher uh, containment index and more accuracy in the spread of the shell. And then for our next ones that we expect is the Kents has the four-prong flower design. It's not very rigid and it's plastic and it's a slightly shorter wad, but we expect it to have better results due to the material of it. Our Winchester, it came with a little shock absorber, so the gunpowder was behind this little piece right here, and the BBs came out at the top up here. It's one of our shorter wads, but the rigidity of the plastic, we expect to have effects in the way the BBs spread. And our last one we expect is the Federal, the Top Gun shell, because just the rigidity of the wad itself, of the plastic, and the quality and price of the shell, we don't expect to be as high as the rest. Here's our test plan. So our procedure, getting there, setting everything up, uh, setting up our stands and whatnot. And then after that, doing the test, we did 3 shots for each shell at two different distances, 20 and 30 yards. Got that data, collected it, interchange, had safety calls in between, and switched the papers in between.
Our setup and measurement tactics consisted of four main parts. The first of which was when we deconstructed the shells, where we manually went in and dissected each of the four shells to examine their internal components. We could really get a good look for what their raw wad was before we test shot all of them, as well as seeing their gunpowder containment and how many BBs may have been in that particular wad. After that, we traced our 15-inch circle that defined our pattern containment zone, what we were actually aiming at when we were shooting at the range. After that, we measured the geometry of each wad before and after test shooting to find differences in the raw wad versus the hot wad. And then the fourth step was counting the individual BBs. So when we came home from test shooting, we took all 24 targets and numbered all the BBs inside and outside of our adjusted circle to get a count for those and to factor into our data tabulation.
For our use of AI, we used Grok AI, which is Twitter's AI. We used it to compare and research different shotgun pattern spread measurement techniques, and the one that came up with and would think we thought would be the most suitable for our presentation is the shotgun pattern containment index. It measures the shotgun spread of BB in the 15 circle target while factoring the BBs that were outside of the sheet. It takes into account the BBs over the total BBs, the standard deviation in those, and then we used an X and Y coordinate system to get the radial distances from the center for each BB inside the target on the sheet itself that we had available.
Now, the first step of our data tabulation process consisted of, like I said earlier, actually going into each individual target and numbering each individual BB. Now, for each target, this could go upwards of 150, 170. Some at the 30-yard distance would be 120 individual BBs that we had to go in and number. We also, if you'll notice on each target, we have a black circle, black 15-inch circle, which was the original target circle. Now, when we came back to tabulate all the data, we readjusted our circle to the pencil drawing, and because we found that we had some accuracy issues at the time of testing, like readjusting on the sandbags or the windy day, or you know, um, missing the target high or low. And by readjusting our circle to the main patterning of BBs, we could get a more accurate accuracy count. And so if you'll notice in each of the readjusted circles, you can see the individually counted BBs. Now we took these BB counts and tabulated them in Google Sheets. And the main part of that was tabulating their X and Y components, which would contribute to their average radius. Um, Once we had made this tabulation for each of the 24 targets, now our example here only goes to 10 pellets, but like I said, they could go upwards of 150 per target. Once we found our X and Y and computed our radius, we could then put it into a graph version, which could much more easily illustrate our shot patterning from the targets. And these X and Y and radius components are what factored into calculating our SPCI.
For our list of test equipment, the top important ones were the safety ones, the safety glasses and earplugs. Earplugs were important due to the fact that we were using a firearm and you can cause permanent hearing damage if not wearing earplugs to protect your hearing. And then our list of equipment, the gun, the shells, a shooting bag to stabilize it, 25 by 30-inch posted paper sheets. That was the biggest paper we could find on the market for the price to make a gridded system as well. Sharpies, tape, cardboard. We tried to use a high frames per second camera, but we're unavailable to get one that was high enough. It needs to be around 180,000 frames per second, and we had one that was 200 frames per second. Our stand setup, measuring tape to get the distances exactly right, and then for our data collections, a vernier caliper and ruler. For our budget, the main items that would need to be purchased were the Gun Club Day Pass, the four different types of bullets. You can see the differences in the cost. The Black Cloud being $42, the Kent's being around $27, and the Winchester and the base Federal model being just under $20 each. And then gun sandbag to stabilize the gun, earplugs, safety measure, safety glasses, and the sheets of paper. The expenses that we incurred as a group and Professor Hoover was generous enough to help us out with were the Messina Rod and Gun Club Day Pass so we could use their facilities, the Black Cloud shells that we did not already have, and then post-it sticky sheet target paper. Generously, Professor Hoover helped us with the target paper and provided us with that. And then the total to us was around $72 with the price of the box of shells and the day passes for each of us. Here's our preliminary schedule and versus our actual schedule when things were completed. You could see the different shells determining what we wanted to use only took us one period instead of two. The acquiring shells took us a little bit longer as we had to go to the armory and order those shells and wait for them to arrive. Removing the wad also took longer as we were waiting for the shells. So we started it, but since we were waiting for that last one, it took a little bit longer. Taking the data was standard as soon as we got the cut it open and got the data, we could tabulate it. The conducting at the range was shorter than expected, as it only took us one day instead of two, and then everything else was on target. Our risk assessment was very high due to the use of a firearm. Main things were handling it properly and making sure everybody was in a safe area and away when somebody was firing it and but safely behind them. For transporting it, we had it in a sleeve with a trigger lock, and the ammunition was in a locked box separate from the one with the firearm inside. Some preventative measures we always treated it as it was loaded. We kept the safety engaged until we were ready to fire. The firearm was pointed downrange at all times, and the use of ear and eye protection for safety and hearing protection was used. No one was downrange when firing, confirmed with range hot and cold calls, communicated with everybody at the testing facility, and then we did not handle the firearm until everybody was clear, away from and behind the shooter, and we only loaded one at a time due to ensure that it wasn't loaded when we went down to change out the sheets, and then in case of emergency we could call 911 or the hospital was down the road.
For our data analysis, we found the SBCI of all of our shells at 20 and 30 yards. Here you can see this is our average SBCI for 20 and 30 yards. The best 20-yard performance was the Federal Black Cloud. It had the highest SBCI at 20 yards of 0.867, while the Kent's Fat Steel had the lowest at 0.681. The best 30-yard performance was the Kent Fast Steel, which performed at 30 yards at 0.672, and the Federal Top Gun was the worst at 0.518. One interesting thing about this slide is the SPCI difference from 20 to 30 yards. The Kent excelled in this department, with the difference being 0.0096 compared to the other shells, which were in the 0.2 range. Primary outcomes and conclusions. The most consistent shell was the Kent Fast Steel 2.0, which showed the least SPCI change between distances, and that indicates a high consistency of patterning. Design influence. Federal Black Cloud's rear opening wad helped to maintain a tight pattern at shorter ranges, but was much less effective at longer ranges. The Kent and Federal Top Gun both used 4-flower designs, but the Kent was much more flexible. The Winchester had a smaller, cushioned 4-flower wad. For our overall trends, wad design significantly affects shot spread performance, with tighter designs excelling at short range and flexibility contributing to consistency. Our uncertainty analysis and some forms of error. It was extremely windy day on the day of testing. We had two different shooters, one for 20 yards, one for 30 yards. The firearm was moving slightly between each shot and had to be readjusted before the next one, which is a big one. And especially for 30 yards, but for both, some BBs missed the target, which affected results. Our future improvements and next steps, using a fixed shooting stand to eliminate firearm movement and ensure consistent aim. Conduct tests at an indoor range to remove environmental variables like wind. Standardized testing setup with the same shooter, a pulley-based target retrieval system for efficiency and consistency. And moving forward, working with ammo companies to create a simple, repeatable way to test shotgun shells could help customers better understand how wads perform and make more confident choices.
Our acknowledgments, we want to first and foremost send a big thank you out to Dr. Hoover for his utmost support throughout the project and throughout the semester and all of his very helpful feedback and criticism that helped propel our project to what it is now. And finally, we'd also like to thank the Messina Rod and Gun Club for allowing us to use their facilities for our testing. And here are our references and bibliography. Thank you very much.